Okay, question number 12 is to construct the molecular orbital diagram for hydrogen, diatomic hydrogen, and then identify its bond order. So first, when you write your molecular orbital diagram, you have a y-axis that shows the increase in energy. And when we have hydrogen, we show how there is sigma bonding involved. And in the middle here, you show the two 1s orbitals for the two hydrogens. And up here, you show sigma star, which is called like the anti-bonding orbital. Then you kind of just connect with dotted lines. And this typically shows where the electrons would go if they formed a hydrogen-hydrogen bond. So for example, let's say we had H2. So obviously hydrogen only has one electron in its atom, so it only has one electron that can participate in the bonds. And we have two hydrogen atoms, so we can show that each hydrogen has one electron. And then these two electrons can come together to form a sigma bond. So then we can draw those two electrons as a sigma bond. And then this is our molecular orbital diagram for diatomic hydrogen. And now we can calculate bond order. So the equation for bond order is the number of bonding electrons minus the number of anti-bonding electrons all divided by 2. So again, we know we have bonding electrons when it's in this sigma orbital, and when it's sigma star, this tells us that we have anti-bonding electrons. So in the case of H2, we have 2 bonding electrons, and we have no electrons in the sigma star, so we are 2 minus 0 divided by 2. So there is a bond order of 1. And there are also no unpaired electrons left in our molecular orbital diagram. So I can also say that this is diamagnetic. If there was an unpaired electron in the final molecular orbital diagram, then it would be considered paramagnetic. Let's see what the junior tutor said. In molecular orbital theory, when atoms create molecules, they generate molecular orbitals classified as bonding orbital or anti-bonding orbitals. These orbitals can be visually represented using an orbital diagram. This representation would be extremely useful in predicting several properties, including bond length, bond strength, and magnetic property. Bond order is a numerical value that could tell us hints about several features of a bond, including the relative bond strength. A high bond order indicates a strong and thus short bond, while for low bond orders, the opposite is true. It is simply half the difference between the number of bonding electrons and anti-bonding electrons. Okay, so they have their equation for bond order. And generally, only orbitals of the same energy can mix together. When the 1s orbitals of two atoms combine, this yields a sigma bonding orbital and a sigma star antibonding orbital. Same scenario happens for two s orbitals. However, for p sublevel orbitals, the molecular orbitals formed are one sigma bonding orbital and a counterpart antibonding orbital sigma star, and two pi bonding orbitals and two counterpart antibonding orbitals. So we didn't have to deal with any of these orbitals, since for hydrogen it only went up to the 1s. Note that the bonding orbital is always more stable and lower in energy than its counterpart antibonding orbital. So since hydrogen has the 1s subshell only, we should expect only two molecular orbitals, sigma 1s and sigma star 1s. So I can also label my diagram to show that this sigma is because of the 1s, and this sigma star is because of 1s. Moreover, the molecule possesses two electrons, one from each hydrogen. Given these, the electrons will be assigned to the molecular orbitals as shown in the orbital diagram below. And based on this, H2 has two bonding electrons and zero non-bonding electrons. I think they mean anti-bonding. Therefore, its bond order must be 1. Okay, so this solution is correct.